Okay, today I'm Ed Seidewitz, and Manas Bajaj and I will be presenting the SysML v2 pilot implementation for both the language and for the API and services. Don't want to spend a lot of time up front. We want to get right into the demo, but I was going to recap a little bit about where we are with SysML v2. I assume most of you have heard about SysML v2, the second version of the OMG systems modeling language. And many of you have probably seen the presentation that was done on Saturday by Sandy Friedenthal, co-lead with me of the SysML v2 submission team on the status. Let me review a little bit what our milestones are. Way back in December 2017, more than 3 years ago now, we had issued the SysML v2 language RFP. And 6 months later in June, we had issued the SysML v2 API and services RFP. The SysML v2 submission team is working on both RFPs together, and we did an initial submission for responding to both of those RFPs in August of last year. Our final submission is coming up. Right now, technically, the date for that submission is in May, but we plan to ask for an extension to August. So we expect that we will have our revised and final submission in August of 2021. Once that is adopted in the OMG process, it becomes what is known as a beta specification and goes into a finalization process. So we expect that to start in the fourth quarter of this year, and the finalization usually takes about a year. That's a process where the beta specification is made public and people can start using it and implementing it and provide feedback, which is then goes into a revision of the specification. So we expect by the end of next year, 2022, that we'll have a finalized version 2.0 specification. In working on this over the last few years, from early on, we decided that we would not just come up with a specification and then figure out how to implement it, that we would implement the specification as we went along. This both provided a proof of concept for what we were designing, and it also allowed us to provide incremental feedback to our user community, which has driven the development of the language over the years. This is now available open source. We have open source repositories on GitHub in the systems modeling organization. The release 2, the SysML v2 release repository is where you can go every month to get our monthly releases. They're released at the beginning of the next month after we developed it. So our current release is the 2020-12 release from December of last year that was released at the beginning of January. We are just wrapping up the 2021-01 release, which should come out in a week or so. If you're interested in the actual development of the language and of the API and services, you can actually see the code in the development repositories, which we have for the SysML v2 pilot implementation and for the API and services. And you can do development installs from those repositories. In addition to the open source repositories, if you install these pilot implementation and try them out and you have questions or want to provide feedback, we have a Google group, the SysML v2 release Google group. It's necessary to request membership in that group. When you request membership, we ask that you provide your name, your affiliation, and reason for interest in SysML v2. We don't really turn people down. We just want to have an idea of who is joining the group. And then once you request that, within a day or two, usually we will accept your request and you can join the group. So today, I'm going to be talking about the pilot implementation, and then we'll go to questions and discussions. Just because of this online venue, what we ask is that people hold their questions until we're done with the presentation portion of the demonstration portion of the presentation. Feel free to put questions into the chat, and we will go to the chat after we do our presentations and go through the questions there. And if we still have time, we can then take live questions. So we'll first do the language pilot implementation demonstration, go to questions and discussions, then Manas will demonstrate the API and services, and we'll end with questions and discussions on that. So let me start with the pilot implementation of the language. This presentation is actually being given out of our Jupyter environment, which some of you may be familiar with. That's Jupyter Jupyter, which is an engineering notebook environment for doing technical studies using typically scripting languages. It started with Python, and now there's a number of languages that can use it. And we fairly early on decided, well, I guess it hasn't been that early on. Last year, we decided to integrate with, year before last, decided to integrate with Jupyter, especially at the urging of JPL, which are big Jupyter users. This has become one of our primary environments for presenting the language to users. It's available as part of the monthly releases and kept updated. What I'm going to do is actually present a Jupyter notebook. This is actually a live Jupyter environment, so you will see cells coming up with the SysML v2 language in it. And we're going to take a little bit of a journey through an example model. It's based on our perennial model of an automotive vehicle. This is a simplification of a model that Sandy Friedenthal and others have been putting together as we go. And it's a good example of how we can use the language to do a typical kind of system engineering modeling effort. Now, I looked back at the presentation we did at IW a year ago, and at the time, we were talking about fairly typical SysML stuff. We were talking about having blocks and having ports and connections, and we just started working on actions and state machines. We obviously still have that. Given the time, I'm not going to talk so much about that though, but some of the new stuff that we've done since then. So we're going to start with looking at requirements and go through a design and look at requirement satisfaction and some of the issues on verification and analysis. We're going to start first though with talking a little bit about quantities and units. One of the things that those of you who are familiar with SysML v1 know is that there's a non-normative annex to SysML v1 called QUDV for quantities, units, dimensions, and values. That was a cut at trying to deal with quantities, with units within systems engineering modeling, which is very important. But there are a lot of limitations to that, and a lot of those limitations were caused by being based on UML. We are now trying to fix those limitations, and we've done a lot of work in developing a library based on ISO standards on having quantities and units. Now, that's not quite complete. We've got a lot in there now. Hans-Peter de Koning has been working on this for quite some time and is still working on it and has most of the ISO standards in there. But there's often cases where you want units that aren't in there yet. And this is an example of how we can construct those. This is using our systems, our actual language, our textual notation for representing models. Obviously, SysML is a graphical language, and it will continue to be a graphical language. But with SysML v2, we've done a lot of work also with the textual language. And one of the reasons for that, to be honest, was because it was easier to get started with our prototype in the textual language. There's a lot of support for doing textual domain-specific languages and workbenches for that, and it's a lot harder to get together a full graphical environment. But that doesn't mean we don't intend also to have a graphical capability for SysML. There are some areas, though, where being able to put things in text is very convenient, especially when it's expression-oriented. And a lot of environments, including Jupyter, are text-based. So you'll see what I'll do here is enter things in text. I'm also going to show you, though, how we can visualize these models graphically now. We don't have a graphical prototype editor yet. That's a little more difficult, but we're getting towards that also. And obviously, we expect production tools to have that capability. So what I'm showing here is a first example of our textual notation. And this is actually a live Jupyter environment. We are importing a bunch of things from our libraries around international standard quantities and the SI units. What I've done here is separately define some new kinds of quantities. This little symbol here is a shorthand for specialization. So I've defined a special kind of quantity called distance per volume. Distance and volume are quantity kinds from our library, and I can actually do arithmetic on them and say that distance per volume is distance divided by volume. I'll be using these later on in the model. So I've just defined them up front in this package, time per distance, volume per distance. You notice the quantities, though, are separate from the units. Obviously, this is a unit I'm going to use to express distance per volume. Kilometers in the library is a unit of distance, and liter is a unit of volume. So I can also do arithmetic on the units, but the units are separated from the quantities. And this is very important. In SysML v1 and QUDV, units were part of the value types, which was a problem because you had type checking that was done at the unit level, where really you want to be able to say this is a distance and express it in whatever units you want: kilometers, meters, miles, feet. What we've done is allowed you to specify attributes in terms of these quantities and put the units on the values that you bind to those attributes. And you'll see that example as we go forward. Now I can actually process this, and it is now parsing and checking it. We don't actually have there's not much to evaluate here. Ultimately, in this Jupyter environment, we want to be able to do evaluation and execution of models. We haven't gotten there yet. Right now, what it does is it actually processes this, parses it. These names are now available to use later in the model. So we have an environment for building models, and as you'll see, we can actually publish this and store it in the repository. We don't have the capability to actually do evaluations and executions yet. That's another thing we want to prototype as we go forward. All right, given that a little introduction to that little bit of notation, let's actually look now. Let's start our journey on exploring this vehicle model. We're going to start with some definitions of requirements. You'll see that the SysML v2 language, as we're proposing it, is very regular in terms of its idea of having definitions, which are things like type-like things, and usages, which are things like properties and attributes. So when we talk about requirements, we can model requirements. We start with requirement definitions, which are templates for specific requirements. Here we have 3 requirements definitions. Obviously, a vehicle would have a lot more requirements. Just going to take 3 simple ones as an example. We're going to start with the vehicle mass requirement. This documentation provides the informal text of the requirement that may be drawn from a requirement document, may be integrated with the requirements management system. Here we're saying that the actual mass of a vehicle shall be less than or equal to the required mass. Now this is a template, a definition. I've decided to keep the actual required mass general as an attributive property of the requirement. So I have actually added into my model here an attribute usage, which is a kind of mass that says the required mass for the vehicle needs to be provided, and then the requirement is the vehicle has to be less than or equal to that required mass. I've done a similar thing here with the vehicle fuel economy requirement that says the vehicle should maintain an average fuel economy that is greater than the required fuel economy. Again, I have the required fuel economy here as an attribute. The engine torque generation is a little more involved. That is a requirement that says the engine of the vehicle has to provide a torque as a function of RPM as shown in the table. You know, if there's a requirements document, you'd have some table and it would show the requirements of it. Well, I want to be able to actually put that into my requirement in my model. So I've defined here a table row that maps rotation to torque. We have some library support for sampled functions like that, but I didn't use it. I just defined it from in itself here for simplicity. Also, I have not specified that this is RPM. RPM is actually a unit. You'll see earlier I defined RPM as 1/minutes. What I'm defining here is rotation as a kind of frequency, and RPM will be a unit of frequency. And then that says for certain frequencies, certain RPM of the engine, I need to provide a torque, and a table is a set of those rows. Now, this is sort of a semi-formal description. The actual requirements themselves are specified in text. I have put in some of the attributes to capture some of the things that parameterize these requirements. What I would like to do is be able to formalize these requirements further. And this is sort of a theme in SysML v2, is that we want to provide the capability to have formal models. We don't necessitate that you formalize it. It is perfectly fine if you decide that for your project and your team that it is enough to have the textual statements, say, of requirements and perhaps tie those to a requirements management system. But if you want to formalize them, we don't want the language to prevent you from doing that. We want the language to enable that and enable tools that will let you do a more formal level of checking. In order to formalize these requirements, we need to be clear on the concept of how we're modeling requirements. In SysML v2, a requirement is considered to be a kind of constraint. It is a constraint on something to meet that requirement. And therefore, we can formalize that by giving an actual definition of the constraint. But in order to do that, I need to first formalize the things that are being constrained. I have these terms in here, not just required mass, but I talk about a vehicle and an engine, but I don't have a formal model of what the vehicle and engine are. Now, you may say that, well, that's part of the design. But in order to even state the requirements more formally, I need what is effectively an ontological vocabulary in order to be able to create the constraints for these requirements. So I'm going to start and at a definitional level, provide definitions of these terms and then formalize the requirements. So first, let me process this. And then what I can show you here is actually our first visualization. So what we have here is a visualization of the requirements, and this shows you it is similar to SysML v1. You can see we've got a requirements definition here in a box. We've got a statement of the requirement, and you can have compartments, in this case, attribute compartments that define or visualize the attributes that are shown here. And we have the familiar screwdriver notation for showing that this requirement def contains an attribute def in it. Now, I should mention that this idea of attributes and attribute defs may not be familiar, but that is our terminology now for value types and values. So instead of value properties, we have attribute usages. Instead of value types, we have attribute definitions, and this is a consistent definition usage terminology, which we adopted really in the middle of last year. And so you'll see that as we go forward, that we no longer have blocks. Believe it or not, we have SysML without blocks. What we have done is said, instead of a block, we're going to talk about parts and part definitions. Right? Blocks were used to define part properties, so they're really definitions of parts. However, if you look at how blocks are used in SysML v1, they're actually used for more than just parts of things. They can be used to define all sorts of things that are similar to what in UML you just use a class to define. And we have separated those ways of using blocks into two things. We have part definitions, but we also have item definitions. Item definitions tend to be things, items are things that, rather than being part of a system, flow through a system. So what I've defined here is two item definitions, one for fuel, which has a certain mass, and another for a fuel command, which has a throttle level. Now, the difference between items and attributes is that items actually have identities, they exist over time. Fuel is a continuous medium, but you can have a quantity of fuel. Fuel can flow around. You don't really consider fuel to be part of a vehicle, but it is an item that flows through a vehicle and powers a vehicle. Fuel command, on the other hand, is a discrete item. It is a command, but you can issue specific commands. You can have two different commands that have the same throttle level. They're still different commands, whereas two throttle levels of 0.5, well, 0.5 is just 0.5. So that's the idea of the semantics of an item. Parts are actually kinds of item. The difference is that a part is something which we distinguish as it's going to be either a system or a part of a system. It has its own identity, but it also can exhibit behavior as an entire system or exhibit behavior within a system. So the vehicle itself we're defining here as a part definition for a vehicle, and we're going to give it certain attributes. Now, just like a block in SysML v1, a part definition can have the entire design and decomposition of the vehicle. But we don't want to do that at this point because we're only defining enough to allow us to be able to define various requirements for the vehicle. What we want is a black box view. Where we've been getting to with the design of SysML v2 is allowing what we call, Sandy Friedenthal coined this, call a usage-focused style of modeling. It's not, again, required to do that, to use SysML v2, but it is enabled, and it is very consistent with looking at a more parts decomposition kind of approach that is typical in systems engineering. So what you'll see is that the definition elements that I show will typically be black box views, whereas the actual part usages are going to show the decomposition. So for now, what we've done is said, given a vehicle as a whole, I can talk about the mass of the vehicle, the dry mass, the cargo mass, the fuel mass, fuel capacity, and a few other things that we're going to be using as attributes. I can also talk about the actions that it performs. I can say that a vehicle performs an action to provide power. Given a fuel command, for simplicity, we're assuming that this is only a two-wheel drive vehicle. So there's the rubber meets the road in two wheel-to-road torques. There's also actions to provide braking, perform a self-test, apply parking brake. These would probably also have in and out parameters, but I'm just not showing them for simplicity in this model. Then we've got a few other things here. A vehicle controller, a fuel tank has a tank mass and capacity and fuel in it. The engine is going to be important for our engine requirement. The engine can generate rotation. And you notice I've specifically called out provide torque. We have a requirement that the engine provide torque, and in providing that torque, that it provide the torque for specific rotations. It provides a certain torque. So I needed to call out a way to talk about the engine providing the torque. Engines can have cylinders, and then there's a few other things that we're going to put together. So I'm obviously, this will be used later on. I haven't shown every requirement that may lead you to need this vocabulary, but you'll notice that none of these things use each other yet. We're just talking about the basic terms, defining the terms. So I have this set of definitions here, and I can actually visualize that. We have the visualization here, and it's starting to look a lot like, say, a BDD. However, you notice that we have some things here that have rounded corners, not square corners. We have in the notation, the graphical notation of SysML v2 made a distinction. Things with square corners are in general definitions. So you can see all these part defs here are in boxes with square corners. But we can actually break out now and show in the notation as actual elements the usages. So we have here perform actions. These are usages of general actions. This performs specific actions to generate rotation and to provide torque. We're going to specify later how it does that. We just want to say it performs those actions. Okay, so moving on, now we're going to go back to the requirements definitions. Given those part definitions, now we can formalize a little bit more completely what we mean by these requirements. Here we've got a requirement definition. That requirement definition states that the actual mass of the vehicle shall be less than or equal to the required mass. Well, now we have a formal model of what a vehicle is, at least a black box view of that vehicle. We can now state that this vehicle mass requirement is about a vehicle in a formal sense. And we do that by specifying the subject of the requirement. So we're saying here that the subject of this requirement is some vehicle. We don't say which vehicle. This is a template, and it'll say given a vehicle and given a required mass, the requirement is that the vehicle mass, and again, we had this as a property of the vehicle, so we can say that the vehicle mass is less than or equal to the required mass. Notice that the expression language is part of SysML v2. In SysML v1, this is something you might do with a constraint block, but when you get down to the constraint block and put the actual constraint in, the expression language is not defined in SysML v1, and different tools provide different expression languages. We have integrated the expression language into SysML v2, and it is consistent with the action model and other calculations that you do. So this is all part of standard SysML v2, or what will be the standard. Notice that this is a definition of a constraint. We have another require keyword here. That's because a requirement can actually not just have requirements. We actually allow a requirement to have assumptions also, and you'll see those added later. So a requirement is specified as a set of constraints. Some of those constraints are required, some are assumed, and the semantics is the requirement is satisfied if a given subject meets all the, if the assumptions are true for a given subject, then the subject must meet all the required constraints. We'll add assumptions a little bit in just a moment. So the fuel economy requirement is also straightforward. The subject here is the vehicle. The average fuel economy has to be greater than the required economy. But the engine torque generation requirement, again, is a little more interesting. In this case, the subject is an engine. We have that table, and the required constraint is a little bit more involved. Now, the notation here, we may work again on adjusting the expression notation, but we adopted a notation that comes from ALF, the action language for FUML, which is the standard action language used with executable UML and is now primarily used really within the SysML v1 community. I mean, maybe not widely used yet, but that seems to be the growing community for it. The notation is actually a combination of object constraint language notation and sort of a more Java C notation for those that are developers. But we may still work on adjusting this notation based on our feedback. But right now, we wanted to try to say backwards compatible as much as possible with the existing alpha notation. So what this says is, given a table, for all rows in that table, the engine must be able to provide a torque for a given rotation that is equal to the torque given in the row. And this is an actual invocation of that provide torque action that is provided by the engine. Okay, so I'm going to process this and show you that also we can now show this just expands our graphical view, and we actually have those constraints shown in the graphical view as well as in the textual view. So now we have requirement definitions. Let's look at our actual requirements. The actual requirements are usages of those requirements definitions. So we're now going to define these actual requirements. We're going to say that the vehicle mass requirement is a kind of vehicle mass requirement. Now, this is a typical convention that the usages have similar or the same name as the definition, but with a lowercase initial letter. This is generally obvious when you're reading the text. It is a little bit harder for me to say the difference between vehicle mass requirement with a local V and vehicle mass requirement with a capital V. So I'll try to be clear when I'm talking about usages versus definitions. In any case, we have a vehicle mass requirement usage here. What we've done is taken the required mass and bound it to 2000. Now, this is interesting. In SysML v2, unlike SysML v1, when you have a usage, the usage actually inherits the properties of its definition, and you can locally redefine them. In SysML v1, you could only do redefinitions when you specialized a block, because that comes from UML, only be able to do that between classes. What we wanted to do with SysML v2, the usage-focused approach, is allow usage-specific redefinitions. So I can now say I have a specific vehicle mass requirement. For that vehicle mass requirement, I redefine required mass. This is a shorthand. You could also use the keyword redefines, but I like the little shorthand symbols that says I am redefining the required mass and binding it to 2000 kilograms. You notice I don't restate the required constraint and I don't restate the subject. Those are both inherited without change. But I am going to add an assumed constraint that we have a full tank of full tank of fuel in the vehicle for this requirement. And I can again formalize that if I want. I can say the vehicle fuel mass is equal to the vehicle fuel capacity, which is our formalization of having a fuel tank of gas, a full tank of gas. For the fuel economy requirements, I'm actually put those together in a group. We probably will eventually have some special notation to distinguish a requirement group from a requirement, but right now we just model a requirement group as a composite requirement. So this requirement group is a composite that has two requirements in it. We actually have two fuel economy requirements for this vehicle. One is a city fuel requirement. The city fuel requirement has 10 kilometers per liter. Now, it was pointed out to me yesterday that in Europe, the standard is usually liters per 100 kilometers, which I know, but our model was initially done with miles per gallon, but I decided to be consistent with SI units, and it was easier to just go to kilometers per liter, so it could go back and forth. You could actually use miles per gallon and kilometers per liter. So given that, what I wanted to show here is you notice that the units are actually put on the value. The required fuel economy is a quantity. That quantity was defined to be distance per volume. I could just as well put in here 25 miles per gallon. 25 miles per gallon would be written this 25 MPG. If I had defined MPG to be miles per gallon, our US units are not entirely worked out. So we don't actually have gallon in our standard yet. We have mile, but not gallon. So that's why I just stuck with SI units for now. We have a highway fuel requirement that has 13 miles per gallon as the requirement there. We also have parameterized this as an assumed cargo mass, which we put in the group as a whole. And in each case, we said these fuel economy requirements the cargo mass is greater than or equal to the assumed cargo mass. Not going to worry about the engine at this point. The engine requirement, for simplicity, we're not going to elaborate that any further. But I will process that, and then we have the visualization here. So you notice that this is visualized using round cornered boxes rather than the square cornered boxes, and we have the definitions shown here inside the definition of the requirement. Other thing to point out is you notice these requirements have IDs. In fact, we can put IDs on anything, any kind of element, but we use the most commonly on requirements. Our language requirements said we had to have them on requirements, and we've sort of more generalized it. This allows these things to be correlated with a requirement ID system, say in a requirements management system. They can be used just like names. I'll be using the name here, but I could refer to this as vehicle requirements ID2 just as well as referring to it as vehicle fuel economy requirements. All right, now we have gone through requirements definition, parts definition. We've shown specific requirements. What I want to do now is do a specific design of the vehicle. I'm going to do that in terms of a parts tree for this vehicle. So I have a part decomposition now for a basic configuration for the vehicle. And we're going to elaborate on this a little more as we go. But the basic configuration for the vehicle now adds in the decomposition of a vehicle. So this is a part decomposition. A vehicle has in it a vehicle controller, a fuel tank, one engine, a transmission, and it actually has two axle assemblies, a front axle assembly and a rear axle assembly. Both of the axle assemblies have axle and each has two wheels, but only the rear axle assembly has a differential. So you notice I am making this decomposition at the part level, and I can actually add specializations at that part level. This axle assembly provides general properties. Every axle assembly has a mass. But what I've done here is said only the rear axle assembly. Only in that case, I can locally add this idea of a differential where I haven't put it here. And that's a very powerful way to have these local specializations. I've also put in some derivations for the various kinds of masses. Really, this one I could have put right up at the definition level because all those were there, that the total mass is equal to the dry mass plus the cargo mass plus the fuel mass. More interestingly, I have here that the dry mass is equal to the sum of the part masses. I've added this in. These are redefined, but this is added in for this usage. I have a set of part masses that are all masses. What I've done is for each of the parts, I've taken the mass of that part and said that it is a subset of the part masses. So this is a set of part masses. What this says is that that one tank mass is one of the part masses. This engine mass is one of the part masses. So this is a shorthand for subsets. This is a subset of one out of those part masses. And then I can sum up the part masses. So again, this is a use of our expression language. Rather than having a separate constraint block, I can easily do these derivations. And this equal sign is actually a binding. It says dry mass is always equal to the sum of the part masses. Let me process this and show you here, we have a parts tree decomposition. And again, this is looking a lot like a BDD, but it's not blocks. This is a part decomposition diagram. And it is showing how that part is decomposed into other parts. So it is very consistent with, say, going into a PLM kind of system on managing hierarchies of parts. So let's look back at our requirements now. We have a very simple initial design configuration in that part model. And we want to say, well, does this design minimally satisfy our requirements? Well, we've got to be a little bit more specific. If we look at our, say, mass requirements, we need to specify certain masses. Well, let's say we give your masses for the parts of this vehicle. We have here vehicle configuration 1. This is a specialization. In general, this is symbol is a specialization, means a kind of specialization. Subsets is a usage level specialization concept. So this is a specialization of the vehicle base configuration. You can see it's redefining each of the parts, and within each of those parts, it is redefining just the masses. Everything else is inherited without change. I'm just specifying the things where I want to bind the masses to specific values. You notice I am not binding the total mass because that is computed. So all these things get added up. I have said that the fuel is at capacity because my requirement had an assumption that the fuel tank was full. So here I have a configuration of a vehicle with very specific masses. Those masses will get rolled up into the total amount. You can add them up if you want, and they should meet they may or may not. I haven't added up the final value. I've made some changes, but they should meet the requirement for the vehicle mass requirement. So I'm asserting here that that vehicle mass requirement is satisfied by this vehicle configuration. Whether or not that's true, a tool could actually evaluate this, do the computation, and let you know. Yes, it satisfies it, or no, it doesn't satisfy it. Is that a valid assertion? Right now, we're not checking that, so I invite you to go ahead and add it up and see if I got it right in this case. And again, we can look at that. This is just another decomposition here. There's actually notation where I could have shown this specialization. It's not shown here because that was defined in another cell, and this is just visualizing what's in this cell. Now that's one way to verify our requirements. We actually do a computation based on our design. And now suppose we go out and actually build a vehicle based on this design. Obviously, it would be a more elaborate design than what we've just shown so far. But suppose we go ahead, have a complete design. We actually build some of these vehicles. How are we going to verify that they meet the requirements? Well, you go out and weigh it. We can actually model the capability to do that. Weighing is a kind of verification, and we model that using what we call a verification case. So here we have, again, a definition first of a vehicle mass test as a kind of verification case. Like a requirement, a case, we have this general idea of case. You'll also see analysis cases in a moment, but a verification case has a subject. It is about something, but it also has an objective. In this case, the objective is to verify a requirement. So we have here the vehicle mass test is, not surprisingly, its subject is a vehicle, and its objective is to verify that vehicle mass requirement. Now I'm going to be more specific here. I'm going to have a specific vehicle mass test, and I'm going to say that this vehicle mass test specifically, this verification case, this usage of this vehicle mass test definition is going to verify or verify the vehicle mass by weighing the vehicle. So it has an action to actually weigh the vehicle in it, and the output of that action is a measured mass. And this measured mass is then assumed to be the overall mass of the vehicle. So I am binding here and saying, let's now take the mass of the vehicle to be equal to that measured mass, and given that, I am going to test if the requirement is satisfied. Now, obviously, a real test case here, you'd have to take into account possible inaccuracies in the measurement, and there'd be a distribution. I'm just going to keep it real simple and basically say, and I take the measured mass as perfect. If the vehicle mass has that measured mass, then I am going to check this requirement on that vehicle. And that's actually something which we can treat as an expression. The verification case has a result. The result of that verification case is what we call a verdict. The verdict isn't just true, false. There's actually 4 kinds of verdicts. This is the same in actually SysML v1, and is taken from the UML profile on testing, which is taken from other common practice. The verdict is pass or fail or inconclusive or error. This is a simple library function in a mathematical sense that says this is a Boolean expression, true or false. If it's true, then consider the verification case to have passed, and if it's false, consider the verification case to have failed. So what this says is check that requirement. If the requirement passes, consider the verification case to have passed, otherwise consider it to be failed. You can model a more complicated way to check this. A verification case could potentially verify multiple requirements. There could be dependencies between the requirements. It could be that some of the requirements have to pass, some of the requirements have to pass if another doesn't. So this could be much more complicated, and it allows the modeler to define what it means to pass the verification case. Going a step further, we can also model not just the verification case, but a system that actually realizes that verification case, carries it out. Verification case is actually an action that can be carried out by a system. We have your definition of the vehicle verification system that's going to use a scale to weigh a vehicle. The vehicle verification system, this specific usage, performs this vehicle mass test. Then, and you can see this is an example of a kind of functional allocation. We have now said the vehicle mass test is being allocated to this vehicle verification system. In doing that, the vehicle mass test has in it this other action to weigh the vehicle, and we have allocated that to the scale. So the system as a whole performs the vehicle mass test, the scale does the weighing of the vehicle. And again, we can visualize that here because we have the definition here. This is an example showing how we have a notation that actually shows graphically that this vehicle mass test is defined by this vehicle mass test usage is defined by this vehicle mass test definition, which has as an objective. And you notice objectives are actually modeled as requirements underneath. The objective is actually a requirement on the vehicle mass test verification case that it should satisfy that objective, which is itself to verify another requirement. That still doesn't tell us whether a specific vehicle has passed or not. We now have a model of what it means to pass, but we haven't really said, do specific vehicles pass or not? We can actually model that now for specific vehicles by modeling what we call individuals. In SysML v1 coming from UML, we had this concept of instance specifications, but it wasn't really clear if an instance specification really was about an instance or possibly a set of instances. It wasn't easy to model object diagrams that had instance specifications on them and how did they relate to objects, so it wasn't really clear what the semantics were. SysML v2, we were supposed to come up with a much more clear, much more consistent way to model what we call individuals and snapshots of those individuals over time, and in fact, how they exist in slices of time. We now have a very specific modeling capability for that, and we can say, well, suppose we have two specific vehicles and we want to record them actually being weighed. We can do that here with this model of individuals. We have test vehicle 1. This is an individual test vehicle that meets the basic configuration. So we inherit all that basic configuration design, and then we are going to bind the mass and say this specific vehicle has a mass of 2,000 kilograms. Test vehicle 2, on the other hand, has a mass of 3,000 kilograms. Now I can do this ahead of time and actually test out my model for verification, or I can actually see this as a model that records, say automatically even, some of the tests that were actually physically done using a real system. So this could be an after the fact record of actual tests that were carried out on real individual vehicles as built. Going forward though with this model, these two test vehicles, I now have an individual test system. That test system meets that specification of the vehicle verification system. It has an individual scale in it. I'm going to define exactly how that scale works, which is, again, a real simplification, right? A real scale could potentially have various errors, and it's not going to be precise. What I'm going to say here is that this scale is perfect. Its measured mass is exactly what we give as the actual known mass of the vehicle, right? So that test vehicle is just going to return the same mass. We are actually working on having capabilities to deal with probability distributions and perhaps doing things like Monte Carlo simulations. Haven't quite gotten that all in yet, but this would be a good place in the future to put that into this demonstration. In any case, this test system now, we have an individual test system with a scale. We want to say that it does 2 tests over its lifetime. It has a slice of its lifetime where this first test occurs. And in that first test, it performs the vehicle mass test on this individual test vehicle 1. So the vehicle that is the subject of this vehicle mass test is vehicle 1. Here we have later, that's what this then means, it's a succession. Test 2 happens later than test 1, and it carries out also a vehicle mass test, but carries it out on vehicle 2. Now you can see, if you work this out, that vehicle 1 actually meets the requirement. It has a mass that is less than or equal to the required mass, which is 2,000. And we, for this vehicle mass requirement, and we can now assert that the vehicle mass requirement is satisfied by test vehicle 1. And not only that, but we can provide a rationale. This is something I put in for this example that we don't have completely in our library yet, but I see this getting into our library for satisfaction. This idea of actually putting in specific rationales, which is something you can do informally in SysML v1. I've been working on how to formalize it. But what I'm saying here is that this is asserted to satisfy vehicle mass requirement because I carried out this vehicle mass test, that test 1 vehicle mass test, and it had a verdict that passed. So I'm asserting that it satisfies this because it passed a test. I'd also like to say, and this has been talked about, a number of people like Michael Vanarchik, who you might know, have specifically requested the capability to assert something doesn't pass a requirement. So ultimately, we'd like to be able to say something like, test vehicle 2, we now know it doesn't pass the requirement. It's not enough not to have satisfy there. We want to specifically have in our model that it doesn't satisfy the requirement. Can't do that yet. Hope to get that in the future. So let's go ahead and process that and move forward. So getting close to wanting to wrap up here, I wanted to show you a couple analysis cases. We're not going to be able to go into detail on this, but another way to verify something is to do an analysis rather than a measurement. So we saw sort of a simple computation of satisfaction based on the design. We saw using a verification case. You can also do an analysis. Now, an analysis can be a way to do verification, can actually be tied into a verification case. You can also separate the analysis. The difference is the verification case produces a verdict. The analysis case, it produces an actual analysis result, which may or may not be used for verification or may be used for other analysis capabilities. What we want to do here is specifically have a fuel economy analysis. That analysis is an analysis case. We define it here. And an analysis case, again, has a subject. Any case has a subject and an objective. The subject is a vehicle, and we're making it specific here to the vehicle-based configuration because we want to do this analysis assuming that specific decomposition. The objective here is specifically to determine that it meets that fuel economy requirement. So we're going to compute in this analysis case the average fuel economy of the vehicle, and our objective is to show that that is equal to the average, the calculated fuel economy is the same as the average fuel economy for that vehicle. Now, that's fairly involved. I don't have all the detail here. Sandy and Hisashi Miyashita have been working on actually elaborating on this, but you can see we can actually put these calculations. These are calculation definitions. You can think of them as mathematical functions. They are not just functions on real numbers, but actually can do computations on unit-based quantities. Here's the key thing. The fuel consumption per distance is computed here based on these individual computations, and we have an actual expression here that is the result of this calculation, and that's actually used here. It's that the calculated fuel economy is 1 over the fuel consumption per distance for that vehicle for a specific scenario. And the idea is we can plug in different scenarios, and those different scenarios here are defined as really a set of waypoints. Ultimately, that position should be a 3-dimensional vector, so you could do something like go to Google Maps and define a journey for this vehicle, a true trip this vehicle takes, and then compute what its fuel economy is over that trip. Okay, and whoops. Finally, or not finally, almost finally, I'm running out of time here, just a couple more minutes. We can do two analyses. So the reason to have those scenarios is that we have both a city scenario and a highway scenario. So we do a trip through the city, a trip through the countryside on the highway, the city economy, excuse me, city economy analysis. The objective here is that we're going to use specifically vehicle configuration 1, and we're going to specialize the objective and say our requirement here is now going to be specifically the city fuel economy requirement. Excuse me. And then the highway fuel economy analysis, we're going to say specifically that the fuel economy requirement is now the highway fuel requirement. And I can assert that the vehicle configuration, that vehicle configuration 1 satisfies both of the vehicle fuel economy requirements that are in that requirements group, because I have two analysis cases that each show that it satisfies the fuel economy requirement both on the city and in the highway. So the last thing I want to show, I'm not going to be able to go into detail, is that we can do also trade-off analyses. So a trade-off analysis, in this case, we have alternative configurations for this vehicle. We are going to plug into our vehicle design a 4-cylinder engine and a 6-cylinder engine. Our engine can have any number of cylinders. In the general design, here we're going to say it's specialized to 4 and specialized to 6. We draw on this trade study definition that comes from our trade studies library. The engine trade-off analysis is a usage of the general trade study definition. It is saying specifically that its objective is to maximize the evaluation of these engines. And we have two evaluation functions, specializations, that says we calculate the evaluation for the vehicle when it has a 4-cylinder engine and when it has a 6-cylinder engine. Obviously, this will be fairly involved, and then we pick the one that maximizes this evaluation, and that's our selected vehicle. And other than having to detail out how to do these calculations, we don't need to say anything more. The whole process of what it means to pick the maximum is encapsulated in just choosing this maximize objective. There's also a minimize objective. If you have more complicated objectives, those can also be specially defined. So that gives you an idea of how we're drawing on our domain libraries to do things that are more complicated, like trade studies. Okay, I am going to wrap up there. The last thing I want to show just in transition is that I process this. We can now take this model. This is in the Jupyter environment. I can now publish it out to the repository. This is using the API that Manas is going to show in a moment. And in doing that, we actually are going to actually write out the model, which I just showed you, write it out, at least the parts tree part of it, write it out to the repository and be able to look at that. We actually have a capability, another capability, and Manas will show some of this. Tom Sawyer has done a visualization tool that reads from the repository and does a visualization client that is a separate visualization implementation outside of the Jupyter environment. But at this point, I am a little bit over time, so I will wrap up there and we can go to some questions for 10-15 minutes. Let's see what we have here in terms of questions. I believe that people can unmute themselves. I'd ask people to stay muted. I'm going to go through the chat. I will see what questions we have. First thing first, how do you do a PPT in Jupyter? There is a plugin for Jupyter called Rise. You can, when you use that Jupyter plugin, it allows you to actually identify things as slides and present them. It's not actually a PowerPoint. It doesn't have all the capabilities, but it's kind of cool to be able to do that live demonstration. Another question from Mudit Mittal is when setting types or setting usages, I see 3 types of syntax being used: colon, the little symbols that I used. Yeah, the colon means typed by or defined by. The colon with a little arrow, that means specialized. So these are actually in our model all kinds of generalization, interestingly enough. So a usage or specialization, say. A usage specializes its definition. So the colon is a relationship between a usage and its definition. The colon greater than is generally specialization. It means it can be done between a usage and a usage, or between a definition and a definition. So it's specialization of the same kinds of things. A colon with the 2 arrows means redefinition. That is a special kind of specialization. So that's a further kind of specialization of a usage. So I can say a usage not only specializes another usage, but redefines it in a certain context. So in UML terms, specialization of a usage is like subsetting it. So if I have something that is defined to have a specific type, I can then subset it to have a more special kind of type. I can say certain of these values of this property have a special kind of type, or I can subset the multiplicity. That in our model is done with this little colon arrow, or you can use the word subsets. Redefinition is again like redefinition in UML, where you can not only say that this subsets it, but I'm actually redefining it in the context. So whereas I had a mass of a vehicle in general defined, if any vehicle can have a mass, I can say in this usage, I can redefine the mass, I can constrain it, I can bind it, and that not only says that this is a specialization of the mass, but that you should consider that now to be the mass property of that vehicle in that context. Question from Ian Phillips on units suitable for IT systems. We do not have those in our standard library right now. Things like MegaBytes, GigaBytes, that would be interesting to put in. Those could be added to the library. We have a very library-based approach. We don't expect we'll get everything into the standard libraries to start with, but we're hoping to enable a robust capability of the community to create new standards going forward. And is there a way to scale units in a standard way? Yes, I actually showed an example of that. We'd like to make the notation a little better. But at the very beginning, I showed that we have a library for the SI, all the standard SI prefixes. We don't have in our library a standard unit for kilowatt. So I defined kilowatt to be basically the kilo prefix times the watt unit. And we're still working out the best way to do that. But all the prefixes are predefined, like kilo, mega, giga, all of them, pico, whatever, nano, femto. So that is all the questions that are in the chat. There's a capability, I think, for people to raise their hands. If you want to raise your hand and ask another question, or if you can't figure that out on Zoom, feel free to go ahead and unmute yourself and ask a further question. I don't see anything else in the chat at this time.
Yeah, and seeing Phillips, just carrying on of the units question. I'm using Cameo, and when I go into the library, you see a rather scattershot set of units in terms of you could have megabytes, but there's no gigabytes or terabytes, or it's defined differently. It's really very haphazard, right? And so I'm hoping what was behind your answer was, there's a 2-part definition. There's a define the basic unit, and then almost automatically you can get everything with the SI prefix.
That is correct. In our library model, we've literally, Hans Peter has gone through the ISO, 80,000, all the parts, and has taken all the unit definitions and generated SysML v2 models for our library based on all those unit definitions. We provide you all the basic units as well as a whole bunch of convenience units. And then we have a separate library of all the standard SI prefixes and a standard way to combine any prefix with any unit. So you can have watts defined and get kilowatts. Now, it turns out kilograms is the standard unit, but you can then define grams as to be 1,000th of a kilogram and then do things like milligrams and whatnot. So yes, that's all there, and it's really at this point just a matter of us working out how to provide a convenient surface syntax to be able to do all of that in a way you'd expect. You can't just put a K on top of in front of the W right now to get kilowatts, because it would just look like a name. You need to do something like kilo times watts, but that may be okay.
Yeah, so I'm just going to volunteer if you want somebody to work on IT units. I'm doing that anyhow.
That would be,
that's the domain I work in. So if you want some help there,
that would be great. We'd love people to start using this. You can either send me an email or you can join the Google group and put a message on the Google group, and we can use that topic for getting you set up and getting any feedback from you.
Okay, good.
That'd be great. I really encourage people who want to provide feedback to join the Google group. We try to provide support there. Remember, this is a prototype effort, and our focus is on actually developing the specification, but we do want people to use it, and we do try to, as we can, provide support if people have issues with installing or using the pilot. But we also want to encourage more community discussion of feedback and getting started on this. We will try to incorporate that into the specification as much as we can. We're coming to our end game on the specification, so we can't do everything. We're gonna have to make decisions. But as I said, we really want to see SysML v2 not as another stopping point for the next 10, 15 years, but a starting point of a vibrant community to create standards, libraries on top of the v2 language. Any other, go ahead.
Sandy, Steve Cash. Ed, sorry. Steve Cash. My experience with this SML or SysML is pretty limited to Sandy's practical guide to SysML. From the standpoint of what you've shown a textual view and a graphical view of the language. Or is it two languages? Is it one languages? Or is there an underlying data structure that really is the language?
The underlying, so what we call the abstract syntax is the underlying definition of the language. So the abstract syntax is basically a data structure for storing models. And that is what's stored in the repository. And you'll see more of that with Manas's presentation.
Okay.
The surface syntax, the graphical syntax, and the textual syntax are both just representations of this abstract syntax. We really want to go beyond that. We want the capability to have more general surface syntax than we had in SysML v1. SysML v1 didn't define the standard textual syntax, defined a graphical syntax that was based on UML and a very specific set of diagrams. We want to go beyond that. We will provide in the standard for backwards compatibility and for commonality a certain set of standard diagrams, but we want to make it very general. We want to allow the capability to define new kinds of diagrams. We want new ways to represent things, tabular views, 3D views, dynamic views. So again, this is something we're not going to get all there in the first standard, but very much we have a language that is defined and can be stored in a repository, and it's set up to allow multiple ways to visualize it. And again, we hope to see a lot of exciting tools coming that will provide those kinds of visualizations.
Thank you.
Is there any chance of conversion SysML and OPM? We look at now, I think there's so much good stuff entering the language that you could see an OPM view over the same information. Yep. Is there any activity between the ISO groups? Because it seems like you've got a wonderful opportunity window now to evolve both cognizant of each other.
That has actually come up, but this isn't being done as an ISO effort. It's being done as an OMG effort. OMG is a group that can provide publicly available standards through ISO. But as an OMG effort, we're not liaising at this time directly with the ISO groups. And we had there are people involved in the effort that are familiar with OPM, but the OPM community has not as such come to the SysML effort. So we really have limited bandwidth to do outreach. So at this point, we've had people come from the Capella community and from the Vitek Genesis, and they're involved and want to connect. We just really haven't anyone from the OPM community come and provide that level of involvement. I don't know. Going forward, yeah, that would make a lot of sense. It's not happening right now. It's a little late in the game, unfortunately. There has been some disconnect, I will say, in the past with OPM folks and OMG, so there may just be some past history that's kept that from happening this time.
With the logical information model, a lot of that history may dissolve because the information is the information and how you get it. I do like the bimodal. We've been looking at, I think we call MIDAS, which is model augmented requirements, which is what you really have here because your requirements are expressed in the context of the model, and therefore it looks kind of, it looks really cool. So we've also used OPM because to date, because it's been very good at conceptual modeling. As you get the detailed modeling, you want to switch over into something like this, but on the front end, sometimes you want a bit. It's conceptual modeling, it's more abstraction and management. But
and I will. UML have had because of the UML background, it's been harder to do that in SysML in the past. And we're probably getting beyond that, and it would make sense. Again, that may be something that happens during the finalization period or even afterwards. One of the things that we're working on now is providing a better language extension capability in SysML v2 than we had with just simple profiles in SysML v1. And we've already looked at the ability to use that to provide an integration with things like Capella and Genesis, where you say, well, Capella and Genesis are still going to exist, but we can provide a semantically equivalent representation within a language extension of SysML v2 that would allow interoperability and interchange. So we could actually notate similar, say, Capella models or Genesis within SysML v2, and when that's mapped to the logical level, it is isomorphic with the underlying data models for those. And I would imagine something could be done with OPM, especially since OPM has a more rigorous semantics, and we can align that now with our more rigorous SysML v2 semantics.
Yeah, we've been mapping OPM to Capella just as an accelerated view because of the conceptual. So as long as you map the semantics down, I think you can. So yeah, if there's any activity in that area, I'd love to join your working group because
yeah, like I said, there is not right now.
Okay.
So again, that should be something if you got on the Google group and proposed that, and you wanted to work on that outside of the SST. I'm not sure we have the bandwidth in the SST right now, but you could start something on that, see who's interested.
Okay.
Who are you? Let's Steve, you're with, who are you with?
I'm Bren Hall. I'm from Honeywell.
Okay.
I think Steve was the other gentleman talking.
Oh, okay. I'm sorry. You're not right. Steve Cash was talking before, and you're sorry. Yes. I'm not sure Honeywell actually is represented on the SST at this point. But certainly if you post something to the Google group, we could see if we could get something going on that.
One more
go ahead.
One more. I'm really interested by by the.
Oh yeah, there's a hand up. I actually see the hand.
Yeah, sorry.
Good for you.
And I'm really interested by the concepts you introduced with a definition and usage, and I think it will be really a game changer. And I was really interested also by the fact you show that we could do decomposition at the usage level, and
yes.
And for nested decomposition and things like that. I think it could be great. My question is, how does it link with the decomposition at the definition level? So what type of rules or inheritance there could be, and potentially the impact on the interfaces, because we define the interface at definition level, but it's connected at the usage level, and when you've got several levels, it goes through usage to definition. So
I have some examples of that. It's actually very consistent. The semantics of the decomposition are the same at the definition and usage level. So if you do your decomposition at the definition level, when you use it, you inherit all that decomposition, but then you can add additional decomposition or redefine it. So it's very consistent between the two. In fact, in our underlying semantics, usages and definitions are actually both kinds of types. So there's this underlying type model, and what we've done is sort of ontologically considered usages, properties to also be kinds of types. So we get a very consistent specialization, redefinition, decomposition semantics across them. So you're right, that is very powerful. That's reflected in the SysML v2 model in a very consistent abstract syntax where we have very consistent definition and usage and terminology. So and as we add things, we've just recently talked about allocation, which is just, we've been capturing some of those. You saw performs, we can exhibit states, but we have a general idea of allocation. We've actually started to capture that semantically. So you can define, have an allocation definition and then show specific allocation usages that actually have a semantic mapping meaning, like between logical and physical levels. So it's very, very powerful and very consistently used now in the SysML v2 language.
And would there be a document that could allow us to have an overview of that type of things without having to go in the detail of the specification, which is probably too much complex, I think, for me?
So you can look at the specification, and there's also a training presentation available. So it's really something, we have a presentation that shows the textual notation and soon also the graphical notation at a user level. The details of how this is structured are really all on the specification right now. And there's not much in between.
Okay, thanks.
Except for a couple papers.
I need to go to the training first, so that's right. Thank you.
Yeah. All right, we should move on now.
Correct, Ed. You should move on.
Sorry, Manas.
Bottom. Let me share
why don't we go ahead and I will stop sharing. And you can start sharing.
You should see my screen now.
You are live.
All right. Hello, everyone. This is part 2 of the session today. My name is Manas Bajaj. I lead track 5, which is deals with APIs and services, part of SysML v2. What I'll be doing today is to take you through a tour very similar to how Ed did with the textual syntax, to give you a flavor of what is the SysML v2 API and how does it work. So with that, I'll make this full screen if I can. All right, so as I said, this is an open session. I'll talk to you a little bit about the background of the API for a couple of slides, and then we'll move into demo, and then we'll talk about how you can learn and contribute more. This is session 2. We had another session, which this is a repeat of yesterday. So the SysML v2 API provides a way for tools and applications to access SysML models in a standard way. For many of you who have dealt with SysML tools and SysML v1 tools, and have tried to do any kind of automation, you probably would have to learn or have had learned an API that was provided by that specific SysML tool provider. And when you wrote application logic, let's say generating a report or anything useful you would like to do with it, you had to write code or make calls specific to that API that was provided by the provider, the tool vendor. And that is great. But when you want to write application logic so that it works across all SysML tools and you don't have to rewrite it for one versus the other, that gets complex. That there's no standard API for SysML v1. And so this is new for SysML. It's also kind of new for OMG. I mean, there have been some instances in the past, but this is going to be, path-breaking in the sense that a standard language is coming out with a standard API. And what that means is provide services, standard set of services to create, update, delete elements, to query and navigate models, to be able to manage models, to do analysis and transmission, and so on and so forth. And more importantly, the idea is that when you would like to automate certain system engineering use cases, such as assessing the impact of a change, which I'll show you today, you should be able to make calls to the API. Every tool provider, every SysML tool vendor who conforms to the API specification will provide their own implementation of the API. So the API is nothing but think of it as a window, as a portal into the SysML model, and different tool vendors can implement that same API using the different technology stack. One would be a relational database, another one could be a document database, another one could be a file-based solution or a graph database, depending on what the technology stack is. So the OMG is not trying to build a piece of software that vendors would have to use. OMG is trying to define the specification for a standard API, and then every vendor, every tool provider would do their own implementation. You'll see a little bit more about it, but the primary API that the SysML v2 submission team is working on are two bindings. There's a REST over HTTP binding, and there's a OSLC binding for the API. So this chart here shows kind of a high-level architecture of how the API is structured. There are two parts of the API. One is called the PIM, the Platform Independent Model, which will become an official OMG spec. And this basically defines the services, what calls you can make for each service, what requests can any piece of software, even your custom scripts that you may write, could send to any provider who implements the API, and what the responses of those calls are going to look like. So basically the request and response definitions, and the inputs and outputs that go with those requests and response conform to the SysML v2 meta model, which we just referred to as abstract syntax. So there is a SysML v2 meta model, which is not dependent on UML, and the API is closely bound to that. So for example, if you make a call to say, get me elements of a certain type, you would get instances of the element class in the meta model or its subtypes. So the IAO, the inputs and outputs of the PIM calls are tied to the meta model. The second layer is called a platform-specific model or platform-specific binding of the API, which means implement those calls, implement those APIs using standard technology. So the SysML v2 submission team is working on these two. There's a REST over HTTP binding of the PIM. There's also an OSLC 3.0 based binding of that PIM, which we call as PSM. So those are the two that we are working on as part of the submission. That will also become part of the official OMG spec. So both the PIM and the two PSMs would be part of the official OMG spec. A tool provider would then take the definitions of the PSM and provide an implementation of that. So within the submission team, we play the role of a tool provider ourselves because we want to verify and test this API ourselves just to make sure it's working. Just like as you saw, the textual syntax, which is part of the SysML v2 language, there's Jupyter-based tooling that track 6 that Ed's been leading and working on, and just to see if the specification is rich enough, is expressive enough, and is it actually implementable. So we do the same thing with the API. The gray box over here shows a pilot implementation where we have put a relational database at the back end to different services, which take that same API, which any tool provider would implement and demonstrate that this actually will work, this actually implementable in any technology stack. Sandy, I think, went through this one on his presentation on Saturday, but I just want to mention that you'll be seeing a lot of these services, the services to query the model, to create the model, to query the model, to version the model, and so on and so forth. I'll be showing the REST over HTTP binding of the API right now. Now, I'll be showing you different tools, a couple of tools. One of the tools that I will be showing you is Postman, which is an API client. Here you will see the raw request for the API. So you'll see two parts when I show you this in a live demo. One that on the top hand side, you will see a request. In this case, the GET request, which means you're trying to fetch an element from the repository. You will see the URL, which is being hit for that request. That will tell you what is the request being sent to the repository using the standard API. And the second part you'll see is a response. So when I make that request, the server or file implementation that we have done would respond to that API request, and you'll see a JSON format for the response here. So keep an eye on these two things: the request that's being sent, what question is being asked to the server using the standard API, and what response the file implementation server is giving us based on that question. If you can focus on that, things will be much clearer. Again, as I said, this tool that I'll be showing you is showing the raw data that is being exchanged from that any tool that implements the API would make to their server and the response they'll get. But before we dive into this one, I'll give you a primer on the first part of the API to show you a little bit of the model and see what you're going to see. So to start with, using the SysML v2 API, it's important to learn some basic concepts. Here's a kind of a high-level overview of the element versioning API model. So you can see the data in a repository conforming to, which is writing the SysML v2 API, is organized in the following manner. you have a concept of a project, which provides a container for the elements that are coming that are in the project. So every element that is being defined using the SysML V2 meta model must belong to a project. Typically, you know the idea of projects. You use this in tools that you use every day, like Jira or GitHub, or Jama or DoorSection or Magic Draw or Rhapsody. All of these tools have the concept of project, and projects are important. Not only they provide containers for elements, but they also provide a way where authentication, authorization, permissions could be set. So it's important to have this definition of project, and SysML V2 API also provides that. The concept of project, a project can have commits. Commits represent the states of a project, the state of a project at a given point in time. Imagine you create a project and you create two or three elements in the project, and the way you would push those elements to the project is to create a commit. And then if you ask the repository using the standard API, get me the elements at that commit, you would get those 2-3 elements that you committed. And so a project can have many commits because the commits show the history of the project as it evolves over time, what elements are being added, what elements are being removed or deleted. So a project can have many commits. Every commit has a change set, which tells you what things were added, removed, or updated in that commit. And so that change set includes a collection of element versions. I'll get to that in a second. And a commit refers to its previous commit. So right now, the versioning model we have in the API is a linear versioning model. So every product has a commit history, and you can think of it as a linked list where every commit points to the previous one, so you can change the commits. We're working on branching model for the API, so you should be able to, in the future, create branches on a project. So every branch can then have its own commit history to allow for more parallel development on a project. But this diagram doesn't show that right now. The concept of an element is right here. So this piece comes to the meta model, the definition of what an element is. But there are two concepts that are wrapping it. So every element is being wrapped in what we call as element version, which represents the state of the element at that point in time, at that commit. That's why it's an element version. And there's an idea of an element identity, which is the version independent representation of an element. So those of you who are coming from a PLM background will appreciate this more than the ALM background. But the idea that in a traditional PLM tool, you would see that you've got the concept of a part master, and then you have part version. So you have the definition of a part, and then you can have a different representation for each version of the part. Similarly, or you have items and item revisions and so on. So here we have the same concept. You have element identity, which represents the element independent of its version. And then that element identity can have many versions, and each version wraps some data for that element, and the data changes from one version to another version. So what's really cool is that I can look at a vehicle, a part, a single element, and I can say, show me all the versions of this specific element using the API, which will be really cool because then you can go to and say, well, this is the history of that one element. This is how it evolved over time. These are the commits at which a new version for that vehicle was created. And here's specifically what had happened at that version. This value, for example, for mass changed in this commit. This value got updated or increased or decreased. You could track and get the full history, not only by project, but by element, because every version of an element is being tracked here. All right, so before I dive into the actual API calls through Postman, just show you the raw data, I want to maybe show you, and this came as a request for Sandy, to show you how a tool would be using the API. I'll show that for a couple of minutes just to get a sense of how a tool would call the API, what you would see in a real SysML tool. But then I'll move quickly back to Postman to show you the actual requests that are happening between the tool and the SysML V2 repository using standard API. So the tool that I'm going to show you right now is here. It is the Syndia application built by Intercax. And here I'm connected to the SysML V2 server right here. If I look at the server, you can see I expanded it. This is how you would get this look and feel of the API in action in the tool. When I expand that server, I get a list of projects. So there's an API call to get all projects, which was made, and you get a listing of projects, and each of them is being rendered at the P icon here. You didn't see the exact call being made, but when I expanded that, the chevron icon, that call was made, the response in JSON was received, and each of the elements in that JSON array was rendered as a project. And you can see Ed's project here, though he actually just pushed a project, the vehicle parts tree example. before before we switched over to me, and you can see his project. And if I expand this project, another call is being made to go from.
It's actually the one further down, Manas.
Oh, it's the sorry, it's the one.
It's the one that says Monday.
Yep, that's one. Yep, thanks, Ed. So you can see that that's the project pushed. It shows February 1st. So then the second call gets made, and I just told you with the API model, from a project you can get to all its commits, and there's only one commit because he did a single push to the repository. Every element he had in the Jupyter notebook was pushed once at the end. So there's a single commit, and you can see from a project you can get a collection of commits. This happens to be a single commit. If you expand that commit, you can see the state of the project at that commit. So it shows you everything, the root elements at that commit. Root elements in SysML v2 API are elements that are not owned by other elements. So these are the top level elements. Now, unlike SysML v1, where you've used to kind of, when you open up a project in any tool, start with a single top level element, and then you kind of start browsing through that, and you get child elements and so on and so forth. In SysML v2, you could have a project could have multiple root elements at a commit, and then which elements are root elements that can change from one commit to another commit. So that allows the modeler to kind of move things around and saying, today I'm designing the wheel, and so the wheel package is my root element. But tomorrow, when the vehicle design starts showing up in the same project, the same model, the vehicle package might become the root element. The wheel might become a child package of that. So you could switch things as you go from one commit to another commit. In particular, I'll pick up one of the packages here called the vehicle parts tree package. And so if I expand that, you can see two icons here for incoming and outgoing relations, and that's how the API works. I'll show you the nuts and bolts in a few seconds. But here I'm saying, give me all the outgoing relationships from this element at that commit, and this makes the call to this using the standard API to get all the outgoing relationships. It gets 2 membership relationships and 1 import, and these don't have a name. So by default, this tool decides to render the UID of that thing here, but other tools may make other choices. Let me go to this one here. So this relationship is from the vehicle parts tree package to the vehicle basic configuration part usage. If I expand that part usage, again, you can see, well, show me all relationships to outgoing or incoming from vehicle basic configuration. And if I query for outgoing relationships, I can see a bunch of feature membership relationships from the part usage. And again, these terms, part usage, feature membership, are all coming from SysML v2 meta model, and you're seeing instances of the data that's in the repository being accessed through a standard API. You just see a tool that is just rendering the data coming from the API. And then from this, I could, let's say, expand. Here I can see the transmission in that vehicle. I could see the rear axle assembly. And if I expand that and look at all of its outgoing relationships, I could then see the rear axle. So very easy. I'm able to just navigate the model at that commit. I start from a project. I look at all of its commits. I pick one of the commits, one of the states of the project. Then from that, I get to the root elements. And from the root elements, I use this API call to get all outgoing relationships. And I can kind of get so-called my model tree or containment tree or element tree, whatever terminology you're used to in your SysML v1 tool that you use today. So that's how a tool would use it. But just to go back to the nuts and bolts, what's happening behind the scenes is the standard API in action. And let me show you some of the same calls I was making through a tool and what's happening behind the scenes. So when I expanded that server and I clicked on it and it fetched me the list of projects, this is what happened. The get projects call was made. This was the standard API endpoint /projects, which was called, and a request was sent to it. And there was a JSON response that our pilot implementation server returned using a standard response structure for the API. And then each of those was taken and rendered in a tree-like fashion on the tool. So that's what's happening behind the scenes, and that's what the standard API going to look like. So here, again, I can pick one of the projects. Let's pick this project called the requirements project as an ID for the project. So I can get all the projects. If I want to get a project from a repository directly through given its ID, I can call another endpoint. Endpoints, is a standard terminology in rest over HTTP APIs, which tells you, the calls you can make. Think of it, if you haven't been exposed to this terminology, these are the calls you can make to any repository through that API. So the API endpoint tells you the calls you're making. So here I have another endpoint, another call I can make and saying, okay, if you do /projects, I'll get all projects. But if I do /project / the ID of the project, I will get that specific project. In this case, it returns that specific requirements project that was created yesterday. If I want to get all the commits in a project, I could do that as well. I could take the ID of the project here, take this ID and say get all commits, and I would just replace the ID here. So get me all projects / the mistake here, projects / so get me all projects at get me this specific project, get me all the commits for that project. If I make that request, I'll get all the commits. In this case, just happens to be one commit. In a few minutes, I'm going to create a new project, so you'll see more of that when you can have how multiple commits would look like. So these are all the commits in this project. And if you have a project with multiple commits, you can query for a head commit, which we'll get back to in a moment when we have a project with multiple commits. You can also get a commit by ID in a project. So if you know the ID of a commit, you could actually query that specific commit in that project. The interesting thing here is that with a commit, you can see the change set. If you want to just get a commit, the details of a specific commit in a project, you could see what things changed in that commit, elements that were updated, elements that were added, and so on and so forth. On the other hand, you can also see the state of the entire project at that commit. So you either can see the changes that happen on a commit over time, or you could see what does my project look like at that commit, which is the full cumulative set of elements at that commit at that point in time. So you could do both. So this commit by ID gets me a commit by a specific ID. What's interesting, which I was showing you, was that when you're at a commit, you could get the root elements of the commit, the top level elements, which are basically not owned by any other element at that commit. And that's usually the starting point for navigation. You just saw me do that when I picked the vehicle parts tree package as the root element. So to get that, I would go to /projects, again, put the ID of the project here as a path parameter, /commits, and I would put the ID of the commit, because the root elements can change from one commit to another commit. In this case, I'll take this specific commit. There's only one commit right now. And if I want to use that as the ID of the commit, there you go. And then /roots, that's the standard API endpoint to get all the commits, all the root elements at that commit in that project. And I would get that and saying, well, that's your root element. There's a namespace element here. There's an attribute definition here, and so on and so forth. There's a package here, which probably is the international system quantities at the root level, and so forth. So you can start with the root element, you can get the root element, and then what I can do is there's a relationship endpoint, which allows me to navigate the relationship, which is exactly what I was showing you in the Syndia tool when I was trying to browse the parts tree. And at the back end, basically you start with an element and you can get all of its outgoing or incoming relationships, and you can do that recursively, and you kind of build you get a model tree. So here, this is my root element, which is this namespace element. I'll take its ID, and I'll go to this endpoint to get me all relationships. And this is how it looks like. You can say, for this project at that commit, for the given element, this specific element whose ID I'm pasting it here, get me all relationships. So again, you are in a project, you are looking at that project at a specific commit, at a specific state, and you're looking at a specific element. In this case, it happens to be the root element of that commit. And then you say, get me all relationships for that root element. And this includes both incoming and outgoing relationships. So what's really cool is that the API is structured as if you're navigating a graph. We really see the SysML v2 meta model, and I went through quite a bit of changes over time to think about this idea of the relationships and elements. All the relationships are also types of elements, but to think of relationships as first-class citizens. And what that enables is that we don't have to create new ways of navigating different types of elements. This idea of just getting a root element and then from the root element being able to navigate relationships and then getting the targets of those relationships and then making that call again and again makes the API very lean and thin, right? You have a very few basic calls you need to really navigate a model which can have hundreds of different types of elements and relationships. And that was central to the design of the API to make sure that we could think of it as a graph, as a bunch of nodes and edges. And if you knew the basic calls, if I'm sitting on a node, I want to get all of its outgoing and incoming edges. And that's exactly what's happening here in the API. I'm sitting in a project at a commit, and I'm asking for that node, that element, get me all of its outgoing and incoming relationships. And it gets me that. It says, well, there's only one. It returns me an array of relationships that element has. There's only one. There's a membership relationship here. And what I could do is I can also be more specific here. Here I ask for all outgoing incoming relationships, but I can also make it particular and saying, get me all of the outgoing relationships or get me all of the incoming relationships. So with that, what you have to do is you have to add this query parameter, which is again a standard thing you would add in any REST or HTTP APIs. Arguments that you want to give, which are optional. If you don't give them, it'll give you all relationships, outgoing, incoming, but you can make it more specific and say direction equal to out or direction equal to in, and that will filter the relationships. So here I'm saying, get me all of the outgoing relationships from that root element. And in this case, it gives me the membership relationship. And now you can see that there's only one outgoing relationship from that root element. So imagine you've just expanded a root level package or root level element in your model tree, and you see one relationship, one outgoing relationship. And you can pick the target of that relationship here. That's the ID of the target of the relationship. And I can just make the same call again. Now, instead of the root element, I'm going to give the target of the relationship as an input and say, get me all of the outgoing relationships from the target. And when I do that, then I see more relationships. Here, I see a membership relationship. I see another membership relationship, which is going to probably going to another package here. Let's look at some others here. This one is going to vehicle requirements package, it seems. So I'll take this relationship and copy its target element of that relationship and make the same call again. This is exactly what was happening when in the Cinder tool I was expanding those elements one by one and showing you the model tree. This exact same call was being made, but with a different ID of the element I was expanding. Now I'm going to say, get me all relationships, outgoing relationships from that element that was the target of the previous relationship. And when I do that, now I start getting specific things. I get more relationships here, and I can keep going on and on. And so you kind of build a model tree here. There's dark generation. There are other elements in here, but you can see this is some raw data coming from the repository. The names of the attributes you see in the raw JSON here are basically defined in the meta model, right? So that's what you're seeing. So documentation or human ID. Well, human ID is coming from the API, but member element, member name, membership owning, namespace. This is all names. It's all coming from the meta model. So you kind of get to see, at a very basic level, an API in action. One from a user-oriented tool, which I showed you, where that you would typically be using, of how to access it, and then down in the nut bolts, what's actually happening. What is the nature of these API calls that are being sent to any repository, any server, and then how the response is coming back. Now, let's try to do something more interesting. Let's create a project from scratch. So if I wanted to create a new project, I would say, hello, let's do another one, INCOSE IW session 2. Let's do that. So here I'm now to create a project. Remember, there's not a get endpoint, but there's a post endpoint. Post endpoints or calls you make when you want to create something. Gets allow you to get something, and post allows you to create something. So here it's a post endpoint. You're saying go to this, go make this call, post a project, and the body will tell you what the input is at. So here I don't need to provide the ID of the project because the server will generate a UUID automatically. But I can just ask it to create a project with this name, INCOSE IW SysML session 2. When I make that call, send that request, I get a response here, 201, which means that the server has fulfilled the request and the resource has been created. The gets would typically give you a 200, or if it is successful, the post will give you a 201 status code, which is a standard REST over HTTP protocol to tell you, well, you can look at the status code and figure out whether the request you sent was successful or not. So in this case, a project was created with this name, INCOSE IW SysML session 2. and a new ID was given to the project. So now I can copy this ID and I can start to create commits, to create new elements in the project. So what I'll do is I'll go to that project, which I've just created, copy the ID over here. And I'm going to go to the server. Again, I'm going to make a new post request, again, because I want to create a commit. And remember that when you create a commit, you have to specify what elements you're adding or removing or updating in that commit. In this case, I'm just adding new elements. It's an empty project right now. So I'm saying, go and create a new commit in this project with this ID. And in the body of that commit, which I'm sending as an input, I'll say that I want to create a new element called vehicle A. And I'm just going to make one change, and that's it. Just vehicle A is all that I would create. So I'll do that here. Remove that. So you can see the change part of the commit is actually, an array which is right here, and includes the list of elements you're adding or removing. In this case, I'm adding one vehicle A of type part definition. Again, that the types are coming from the SysML v2 meta model. And it's this project. This is a containing project. So I'll copy over that and say that's the project in which this element is going to be created. And there are no previous commits. This is the first commit. So I'll remove this and say, well, this is the first commit. There's no previous commit. And when I send that request, I'll get a response again at 201. And you can see the server actually created a new commit in the project with this change set. Now, I just provided only the name for the part definition, but any part definition element can have tons of other properties. And I just sent the name that only that was populated. But the other properties, which again are coming from the model, were not populated. They're just empty. I could do a future commit later on where I could populate those other properties too. But you can see there's only one element that's being populated here. And the commit that was created has its own ID now. So I can copy that and I can create another commit. So this time, I will say that I'm going to create a new commit where now the previous commit is the commit that we just created. So I can now chain together the commits. And this is exactly what a tool would do. You are just seeing the backend chatter or the data that I'm sending to the server and getting a response back. But a tool in its UI would be making the same thing. You would probably get a form which would say, what are the elements you're creating? And it'll automatically fill these pieces out for you. But I'm just showing you what's happening in the API at the backend. And in this commit, I'm going to create more elements, not just a vehicle A, but I like to copy this and say, okay, I'm going to create vehicle B. And I'll also copy this part of the chain set and say, let's create another vehicle C in here. So in this commit, I'm going to send again a request to the same server to create a new commit. And it'll be vehicle B and vehicle C. And this is the previous commit. I'll send the request here and I'll get a 201 response. Again, two more part definitions, vehicle B and vehicle C have been created. As you can see, this is the first one. That was vehicle C. And this is, again, vehicle B and vehicle C coming on here. So now what I can do is I can now show you what does it look when you have multiple commits. So if I go to that project which I was using, let's go to our project here, that the new project we created. I copy its ID here, and I get to get all commits in a project. If I get to this ID and hit send, I'll see two commits because remember we made two commits. The first one was the first commit didn't have any previous commits, and this is where we created vehicle A. And the second one is the one where we created vehicle B, and this commit shows the previous commit as its the one from previously as its predecessor. So I can now see different commits. And if I ask what is the head commit is the latest commit. Sometimes you don't care about the entire history of the project. You just want to get to the latest version, state of the project, and just ask questions. And so if you want to get the head commit, you just do project / the project ID / head, and that'll give you the head commit, which is the latest commit. Or which is basically the head of the commit history. That's what it means, the head and the tail of a linked list. So that's the head commit. And you see that one. And then if you want to get, if you want to see that specific commit, you can actually get that's, the details. You can see the details of that commit. Remember, we only added two vehicles, B and C. So I should be able to see a chain set for that commit. What happened in the commit? So I can go to this endpoint, the previous one. See, so I'll copy the project ID from here, and I'll say, okay, for this project with this ID, and for this commit in that project with this ID, I would like you to tell me the details of that commit. And I'm going to send a request. It tells me, yep, in that commit, the change set includes, 2 changes. You can see 2 sub-JSONs in here. One was this vehicle B, vehicle C got added, and one was this, the other one was the vehicle B was added, and that you can see over here. So we see the 2 changes out here. Now, if I want to know all the elements in a project at a specific commit, which is what we were seeing here, let me see if I can show you in the tool now. So if I go, there's that hello INCOSE IW session 2 project created right here. You can see the 2 commits here. The first commit just had vehicle A, and then you can see vehicle A, B, and C in the second commit. So you can do both. You could do get the elements that change in a commit, and you can get all the elements in the project at that commit. This is showing the latter. It's showing you all the elements in the project at that commit. Only vehicle A was there in the first commit. Now you can see A, B, and C in the second commit. So hopefully that gives you a flavor. All right, in the interest of time, we'll move on, coming to the last phase of this. There's also a query API in the SysML v2 JSON model. Without going into much details, I'll just mention on it that you can actually create a query with select clause and telling you what attributes you want in the responses. With specific constraints, you allow for primitive constraints, like, for example, give me all elements with type with name equal to a certain name, or you can create complex composite constraints, which is which are joins of primitive constraints or other composite constraints using and or operators. And so this is also allowed, and you actually have a way. We actually have a way to create queries and actually then execute the query. So the 2-step process, you can actually create a library of queries for a project. These could be common questions you ask on a regular basis. So you would keep on creating new queries, and then you could persist them, and you can get a query by a specific ID. And then in an automated fashion, you could execute those queries, set up a cron job or some sort of automation tool to run those queries on a daily basis to get results from the model. And that's also available here. So here, for example, when I try to create a new query, or if I want to get all the queries in a project, I could see in this part, I have a few queries already created. I'll skip to the last one. Here's one which says, get me this query where with this ID, which says, well, I want to get all the elements whose name is a reliability requirement. So there's only one where clause. It's a primitive constraint, not a composite constraint, and name equal reliability requirement. You can also do inverses. Sometimes it's easier to write constraints as using the not operator, and that's what it does. So here, and then so I can get all the queries in a project and create it. And then I went on to execute it. I just go to this endpoint that says, for this project, I want you to execute this specific query and give me the results. And when you do that, it makes a call to the server, and it'll fetch you that element with the name reliability requirement, and you get the ID of the element. And let's say then at this point, you want to say, well, let me see, what is this thing connected to? What are other things that this reliability requirement is related to? Well, you know how to do that. You would just go to the relationship endpoint, and you would start to see, for this element in this project at that commit, start showing me all relationships outgoing, incoming, and you can kind of come out, build your own tree, like I was showing you in this India too. So that's very easy to do. So you get the flavor of that. Let me come back here to something else. So the other important thing that we want to mention is that not only you can do these primitive calls to the API, but you can actually use these APIs to do something more significant. So we've tried to look at some functional threads that you could address using the API. So one of the functional threads is to do impact analysis. So if you make a commit in a project, you can determine what elements change in the commit. And from the elements that change in the commit, you can use the relationship endpoint to figure out, well, what requirements need to be reevaluated because something in the design has changed? And what analyses would I run to reevaluate those requirements? And so I'll show you a couple of slides here. This is the vehicle parts tree example that part of it that Sandy had pushed earlier, but Ed, I think, showed a similar version of it. But here's a model which has requirements in it, and you can see the requirements for the vehicle fuel economy and the engine specification. And then you can see this definition of a vehicle configuration, and there's a satisfy relationship in here. It says the vehicle satisfies the mass requirement. So what happens is if I change the vehicle design, I can look at the same parts tree I was showing you in the Cinder tool or any other tool to navigate my relationships, or I can call it through the REST API in a raw form through Postman and do this many times. But given vehicle B, let's say the vehicle B changes, I can trace through those relationships and navigate to which requirements need to be evaluated. In this case, I can trace it myself and say, well, that vehicle B has multiple or single satisfy requirement relationship to the vehicle mass requirement. And given the vehicle mass requirement or the vehicle fuel economy requirement that may get affected, you can trace those relationships and come to the specific analyses that we need to run. So in this model, there was a fuel economy analysis defined, which said the objective of the analysis is to determine if the fuel economy requirement is being satisfied by vehicle B, which is the subject of the analysis. So not only you could say that, okay, if I change the vehicle B, what requirements may need to be reassessed or reevaluated? You can go back, you can trace your way back through it. And then for every requirement, there might be a different analyses that you may need to run. And so you can trace those analyses and run them. So the second part of this shows you exactly that given any requirement, I can trace myself back to the analyses whose objective was to reevaluate those requirements. So you can navigate these functional, navigate the model through these relationship endpoints that I've shown you to start to address some of these key system engineering use cases. Now I'll come to the end of my presentation here. What you just saw, I didn't show you the Tom server visualization, but what you just saw is that there are 5 tools that you saw today, almost 5 tools except for this one right now. They were all developed and managed by different organizations. The requests that we were sending were to the SysML v2 pilot implementation, which was written with PostgreSQL relational database stack technology. You saw Ed using Jupyter environment, which is using the publish command to publish to the API right here. You saw me use Postman to make requests to the server using standard API, get a response back. You saw Cynthia being, show you render the parts tree or that model tree. And Tom Sawyer did this as the same thing, it consumes the API as well. You see 5 tools written by 5 different vendors or 5 different groups of organizations, some open source, some commercial. And they have their own technology stack, their own kinds of databases, and they're communicating peacefully, fine through a standard API. This is a microcosm of what we think is going to happen when you take this to a large enterprise, and you have lots of different SysML v2 API providers, not one tool, but you may have many different tools that are providing that being used in your organization to build SysML v2 models, and they're all providers of the API. And you would have not 1 or 2, but hundreds of consumers of the API, some for report generation, some custom plugins that some 1 or 2 individual users would have written, and some could be like dashboard that a company may have invested in. And they could all communicate just fine through the standard API without you having to write that business logic again and again. Tomorrow, when a new SysML tool, provider tool enters your organization, hey, theoretically speaking, if they implement the API, your existing dashboards and query tools that you may have written should just work fine through the standard API. So this is the promise that we are trying to evaluate, and whether we can live up to that. But this is the goal of the standard API. With that, I'll end, and I'll open up for any questions you have at this point. Let me see if there are any questions in the chat window.
Yeah, it looks like there's one in the chat window.
Let's see it. Takes a few seconds to get to the chat window once you're sharing. Let me see.
Okay, it says, will OSLC 3.0 have a dedicated SysML v2 vocabulary in addition to current AM1?
I think that was evaluated. So I think the idea was to just provide the AM and the RM service implementations because a lot of the tools are already there that can consume any AM provider, architecture management service provider, or a requirement management service provider. So the decision was taken to just do that as a starting point. But I think there's no effort right now to build the entire SysML v2 meta model as a resource shape using a new OSLC specification. But the pilot implementation that is being done, which is being led by Jadil Khoury at KTH and Jim Amston at IBM, they have been looking at a much more thorough implementation, which exposed was more of the vocabulary. That's still under review. In the initial intent was to just use the AM and the RM spec as it, because they have a lot more tools that already confirm with that. And there's also CM, the configuration management service, which could be a provider or a hook into the versioning and the branching capabilities that are coming into the API. Let's see the other. So if the reliability requirement is not met, does it flag it? Yeah. So ideally that would be the only thing. In this case, what I showed you, the call was tracing through and saying, well, these are the requirements that may get affected. They'll need to be reevaluated. And you saw me trace to a specific analysis from a requirement. So now if we have the analysis tool in place, then ideally you should be able to make a REST API request to that analysis to execute the analysis, get the results back, and verify if the requirement is being met or not.
Anyone else? I don't see any hands up.
Yeah, me neither.
Okay.
Well,
if there are no further questions, we can wrap up there. Anything else you wanted to add, Manas?
no, I'm good. I just recommend people to use the Google group. Oh, I did want to add something. Hold on. Ed, thanks for asking. One slide I did want to show, seeing if there was time for it, is how you can contribute, and I could learn more. So we do invite vendors to step up and become providers of SysML v2 API service. Some of the vendors are involved, some more, some less. We encourage everyone to participate in the track 5 and work through it. But we also invite users. If you want to try the open source release, it's up on the GitHub repository. The system modeling organization that we created has multiple repositories. You can see the one for API and services. You can actually download and set up your own SysML v2 repository. You can use the REST API through Postman, or you can use a Java and a Python client that has been published there. Explore the API and use the Google group to interact with us.
Okay, and with that, we thank everybody for attending the session, and we look forward to having you give us feedback on the implementation as we move forward.